Good morning again, AP Statistics. Day 10. We still have some things to learn, and I figured it wouldn't be a bad idea to re-show you some of the same ideas. Most people need to see this stuff 2, 3, or 4 times before they really get it down. So some reminders. We're still working on inference. That means to make an educated guess about something without having all of the information. And specifically now we're working on confidence intervals. And I'll give a couple examples of those today. Let's take a look at an example about commute or drive times, how long you drive into work or school, things like that. The population of drive times is definitely not normally distributed. There are some people, unfortunately, drive to Detroit from Lansing or even further, and they have some really high drive times, whereas I'm way down here about 8 minutes, and lucky me. So the population, let's just say, has a mean of about 25 minutes with a standard deviation of 20 minutes, and that's what that shape looks like. That's not normal. However, if we decide to take a sample size, let's say 64, because it's a nice number, and find the mean of a bunch of different samples, in fact, every sample you could ever take, you'll be producing the sampling distribution. We already know this. The central limit theorem says that the mean of the population and the mean of the sampling distribution, they are the same. The central limit theorem says if you take a large enough sample, the sampling distribution will be normal, even though the population was not normal. One of our rules also says if you take a small enough sample, and as long as 64 is less than 1/10 of all the drivers out there, and I'm sure there's at least 640 drivers, then we can use this approximate formula for the standard deviation of the sampling distribution. So those are things we already know from the central limit theorem. So this is what the sampling distribution looks like. And here's what this says. If 68% of my samples, remember the 68, 95, 99.7 rule, 68% of my sample means are going to come back within one standard deviation of the true mean, so between 22.5 and 27.5. We also know if we move out 2 standard deviations from the mean, that 95% of our sample means will come within somewhere between 20 and 30, and that's not real far from the real answer. Let me say that again. 95% of the time, when we take a sample, we come and plop it down, it's going to come within 2 standard deviations of the real mean. The problem is that's not how statisticians like to look at things. We understand 95% of the time you go get your sample, you bring it back, you put it down, and it's within 2 standard deviations of the real mean. We like to turn this statement around. We don't want to know how close our sample mean is to the real thing. We want to know how close is the real thing to our sample means, what's more important for us. So here's the idea. If you come back with a sample mean, let's say right there, that's a pretty probable sample mean, and you extend 2 standard deviations, which in this case is worth about 5 minutes. If you do that, you form what's called a confidence interval. And lo and behold, within this confidence interval, there's the real population mean. I could do another one over here, and if I extend 2 standard deviations either side of that, lo and behold, within this confidence interval is the true mean. It happens most of the time. In fact, only if you get what we might call a bad sample, way over here somewhere. If I got a sample way over there and extended 2 standard deviations either side of that, I would not encompass, encapsulate, trap, however you want to say it, the true mean, because that was so far out. The good thing is, samples like this only happen when you end up outside either one of these, and as we know, if this encapsulates 95% of the samples, then the only time you're going to be out in the fringes here and get a confidence interval that doesn't encapsulate the true mean is 5% of the time. It doesn't happen very often. If you go 2 standard deviations either side of your sample mean, that will always be true. So what we look at, if we go grab sample means, what we want to know is how often, when I extend this far one way and this far other way, and sort of put down a net, so to speak, how often do I snare the true mean? And the answer is, if you go 2 standard deviations from your sample mean, that will happen 95% of the time. Let's take a look at another example. And we're going to take a look at an example this time where we don't know the true population mean. I mean, an example where we do, let's go with one where we don't. And as I pointed out yesterday, one of the strange things in this chapter, you're going to have to get used to not knowing the true population mean, but somehow we do know the standard deviation of the population. Again, we'll take care of that in later chapters, so bear with me one thing at a time. So now we want to know, a lot of you guys are going to college next year, not everybody, but many of you. What's the average amount that we spend on college books? So we go take a sample size 100. Our sample mean happens to tell us it's 370. Now, we think in the back of our head, well gosh, the real answer is likely somewhere around 370. And actually, I gotta be careful with that wording. It either is or it's not. We'll work on that as well. We know that the standard deviation of the population is 120. If we want to form a 90% confidence interval rather than a 95% confidence interval, the idea is the same. We just won't travel exactly the same distance either side. So here's what we'll do. A confidence interval is always based on the best information that you have. Your sample mean, that's the best information that you have, so center your whole confidence interval around the best information that you have. Over here, we decided if you wanted to make a 95% confidence interval, you should go 2 standard deviations either side of your sample mean. Over here, because we want to form a 90% confidence interval, I'm not going to put a 2 in there. I am going to put this in here. And by the way, we should always stop, as some of us did this on the test and some of us didn't. What 3 assumptions am I making? I'm assuming 1, that my sample mean on average equals the population mean. I'm assuming that my sample mean is an unbiased estimator. I drew this picture, and it looks very normal to me, so I also must be assuming that the sampling distribution is normally distributed. That's okay because I took a large enough sample. I also need to make the assumption that I can use this formula only under the conditions that I took a small sample. So as long as my sample size of 100 is less than 1/10 of the population size, so as long as there's, 1,000 college students out there, and I'm pretty sure that's true, then I am justified in using that formula for the standard deviation of the sampling distribution. Our question still remains is how far to go. Not 2 standard deviations, that's only for a 95% confidence interval. And here's the thought. If I want to be less confident, only 90% confident, again, it's like the dartboard. The closer in I move, the less confident I become. 10% confident maybe of hitting this, if it's a dartboard, maybe I'm 30% confident hitting here, maybe I'm 70% here, maybe I'm 9% confident hitting there. But the idea is that the confidence and how big your target are, they grow and wane together. Here's a way to find out how many standard deviations to go. It's not 2 this time. If you look at a normal distribution and you want to encapsulate 90% of the population rather than 95%, you have to understand that makes this the 95th percentile, and that makes this the 5th percentile. That leaves 5% here, 5% here, total of 10%, which does leave 90% in the middle. You have to look in Table A in the front of your book and look around for the 5th percentile of 0.05, and if you do that, you're going to find a z-score of negative 1.65. Alternatively, you could look in the front of your book and find 0.95 on your table instead. Miraculously, z equals positive 1.65 instead. So what that means is rather than going 2 standard deviations as I did over here for a 95% confidence interval, I'm going to put 1.65 in here. Again, if I'm less confident, I can make a smaller target, just like I said in here. If I do the math, this piece right here just happens to be worth 19.8, roughly $20. In fact, it might even be look at it easier to go, hey, our confidence interval is 370 plus or minus about 20. So our confidence interval reaches from 370 down 20 from 350. 370 plus 20 is about 390. We are 90% confident that the true average amount spent on college books by students is between $350 and $390. Again, be careful. People are tempted to say, oh, there's a 90% chance that the true amount of books is between $350 and $390. And as we talked about yesterday, you can't make that statement. The true mean either is between $350 and $390 or it's not. There are no chances. Just because we don't know what the answer is, you still cannot associate a probability with something that either already is or already is not true. We are 95% confident that the true mean is between 350 and 390. If someone asks you what that means, you're supposed to say something like, well, if I use this method, then 90 times out of 100, if I take my sample mean and go 1.65 standard deviations either side of that, 90% of the time, the true population mean will be somewhere within that confidence interval that I just constructed. I know that's a lot of words, we'll get used to it. Something that I did want you to recognize, all confidence intervals are built the same way. We started with the sample mean. We always do that. It's the best information that you have. And you build your confidence interval around the best information that you have. You always go up and down. As long as you have met this condition that your sample size is less than 10% of the population size, you are allowed to use this. This little Z star thing just means how many standard deviations you want to go. Sometimes it's 1.65, sometimes it's 2. If for some reason you only wanted to form a 68% confidence interval, that's very strange, but you could, well, then you'd only go 1 standard deviation either side of the sample mean. And when they're all built the same, this piece on the end is called the margin of error. It gives an indication of how far off you think you could be, even though the answer is definitely already etched in stone. So this is in your book. In fact, this is even on your formula page, I believe. They talk about they don't call it X bar, they call it the statistic. Because in the future, this could also be replaced by p hat. We could do the same kind of thing with proportions. We would still go plus or minus, it would still be Z star, but you wouldn't be able to use this formula if you're looking for a confidence interval for proportions. You would simply replace it by the formula that we have used already for the standard deviation for sampling proportions. Same kind of information as yesterday, a little bit faster. Hopefully you're getting better at this, and I hope that I will see you tomorrow. I'm going to send you another short homework assignment. Please keep up. Thank you.